So on Monday, when we did our analysis of variance, we were looking for the differences afforded by one change. In our chip manufacturing example, it was which plant are we at? In the example about GPAs, it was which major am I in? And I was able to say, oh, while there is some variance, there is a clear difference between these two plants and these other two plants. The averages are not the same across the entire thing. There is some variation. But that's one factor. What do you think this is? So I've got two different things that affect the change, right? Now, the without replication part means I only get one data point for each combination of the two factors. So I could have a bunch of different factors, say A and B. I promise the reasons for the subscripts will become obvious in a minute. I have A1 through AR and B1 through BC, and they affect my response variable Y. And I only get one possible sample for each combination. So I'm going to write out the combinations in a table. I'll list all the factors A in rows, AR, the number of rows I've got, B1 through BC in columns. And then for each possible combination, I will get a sample. The first A factor, the first B factor. Let me actually write in B2 and A2. So I'll have Y21 here and Y12 there and Y22 there. And all of these are in the first column. So down here I get YR1 and YR2 because those are all on the second column. And then by the time I get here, that's Y1C, Y2C, all the way down to YRC. And the subscripts go with the row number and the column number, RC, in that order. But now I can think about averages. I can do averages across a row. I can do averages down a column. So I'll get a whole bunch of different averages. I'll get averages for each row. Now notice that I gave those subscripts 1 dot, 2 dot, because it's row 1, but there's no column count anymore. And when I do column averages, I'll get Y dot 1, because I'm no longer caring about the row. Y dot 2, all the way over to Y dot C. And then somewhere, if I took the average of everything, I'd have one overall average. We're going to call that the grand mean. That's the average of all the numbers in the entire table of factors. So this is the way we lay out our data for our ANOVA without replication. There's only one number in each possible combination of A's and B's, each treatment that is a combination of factors. All right. Again, if my null hypothesis is correct, I want to have a null hypothesis for the factors A and a null hypothesis for the factors B. So I'm hoping that all of the results are equal. My null hypothesis should be A doesn't make a difference. B doesn't make a difference. There's no difference between the rows. There's no difference between the columns. These are unaffected by which row we are in. These are unaffected by which column we are in. That's my null hypothesis. Status quo, everything's hunky-dory, everything's equal. What's the alternate hypothesis? At least one of them somewhere is not equal. If I think of this the way I was thinking of the ANOVA we did on Monday, I could write this like the equation for a line, that linear function idea that we had. Only now I'm expecting some sort of reaction for the A and some sort of reaction for the B, so I get a more complicated model. If my null hypothesis is true, then every plant is equal. Every major is equal. It doesn't really affect what's coming out in my response variable. Again, my big problem here is the same problem I had previously. I have a lot of distinct algebraic calculations that have to be done. I mean, on page 430, we see, oh my God, I have to take into account every row sum and there are degrees of freedom for each row. I have to do every column sum, there are degrees of freedom for that. I have to do the possible errors, and there's a square for, oh God. I'm going to say this absolutely 100% of the time. I never want to do this. There is absolutely no reason on God's green earth for me to do this by hand. I'm going to do all this crap in Excel, which means we come down to the same question that we had on Monday. How do I know what the answer is once Excel does the work? But notice what I end up with here at the end. I end up with F values. And this time there are two of them. Why are there two? Two factors? No, not even tails. I got two factors. I got the A question, are the A's going to affect anything? And I got the B question, are the B's going to affect anything? So really, this null hypothesis that we wrote down isn't one hypothesis. It's one for the A's and a separate one for the B's. So I'm really doing two F tests at once. And that means I'm going to get two p-values. And each of those p-values will tell me whether or not to accept or reject the corresponding null hypothesis. Questions? Because this is all set up at the moment. Now, sometimes in ANOVA testing, really, I'm only interested in one of these two factors. But the other one is there just in case there are confounding effects. All right, wait a minute. This is an idea that we really should have mentioned in passing earlier. We didn't. But way back in chapter 1 and chapter 2, talked about coming up with reasonable questions, right? And coming up with a good experimental design, and getting a good question is just as important as figuring out what your good data tells you. I claim your ability to palm a basketball is connected to your score on an IQ test. Now, most of you at this point are going, bullshit. Good. Good. But why is it bullshit? I have a response variable, your score on a STEM IQ test. And I'm claiming there are two different factors. Whether or not you can palm a basketball should be one of them. No. You see, what happens is I give college students IQ tests. Some of them can palm a basketball. I give the same test to a bunch of fourth graders. How many of them can palm a basketball? Why? Because they're little kids and their hands aren't big enough. A confounding factor. Something that's actually not relevant, but kind of looks like it could be. It is quite reasonable to set up an ANOVA with two factors where you really only care about one of them. So what I could do is I could add to my second factor, instead of can you palm a basketball, it could be something like age. And that would control for the difference, right? And you will often hear such a thing called a randomized block model. An ANOVA with a randomized block. Almost always our blocks then become our rows. And our columns, those are the factors we care about. In which case, we're really only testing for the B hypothesis. The A hypothesis is kind of there as a stalking horse. And in this case, we'll really only look at one of the two F tests rather than both of them. But that almost makes a two-factor ANOVA kind of being a one-factor in disguise. It's a great idea, but at the moment it doesn't make a damn bit of sense. So let's do an example and walk our way through this. Ready? Page 433, problem number 21. Concerned about Friday absenteeism, management examined absenteeism rates for the last 3 Fridays in 4 different plants. Does this sample provide sufficient evidence to conclude that there is a difference in which plant treatment means? Okay. 2 pieces of important thing. All I want to know is if where you are changes your absenteeism rate on Friday. plant 1 versus 2 versus 3 versus 4. My control is that I didn't just pick one Friday. I picked 3 different Fridays. I don't know. Maybe there was a football game in town on Friday night, and it was important and everybody went, or maybe there was a concert in town one Friday night and everybody went. So I picked 3 different Fridays just to make sure. So which row I'm in is less important. That's the block idea. The treatments are the columns. So I'm going to pull up this data set in Excel and walk us through exactly the same ideas we did on Friday. The data set in question is absences. Chapter 11, exercises, absences. Absenteeism at 4 plants. Now notice, I only have one data value in each block. That's my without replication idea. March 4th, plant 1, 19 people were out, and so on. So I want to create an ANOVA. I've highlighted this table right here. I go to data, data analysis. Where was my ANOVA stuff? All the way up. Now notice, single factor was the very first one. There are 2 different 2 factors. One am I doing? Without replication. 1 per box. 2 factor without replication. Poof. It asks me, where's your data? So I go over here and I say, oh yeah, my data is right here. Yes, there are labels on this information. Oh, wait a second. That's my data. Plant 1, 2, 3, and 4 are the labels. I don't need the word location at the top, I think. So I took that off. Enter. What did they say? They said, do these provide evidence? Now that means I get to decide how significant I want this. I need my alpha. And if there's no particular reason not to, I might as well use 0.05. That's what's in there already. I'll use that. Make the data, put it on a new worksheet ply. Go. I said go. There we are. Lots of stuff here, right? All right. Now there's a lot of information in this result. Sorry? This particular file is named absences. In the chapter 11 file under exercises, it should be absences. What does this tell me? Let me start up at the top here. That's summary information. On March 4th, there were 4 plants looked at. The average and the variance and the sum are all there. So those first 3 columns, sorry, the first 3 rows here, that tells me what happened across each row. But the rows don't matter very much. Was there a difference week to week in absences? Yes. I really don't care about the difference week to week. I care about the difference plant to plant. So I want to look at these. Is there a difference plant to plant? There's a difference. Is it statistically significant? 2 different ways to answer the question. My null hypothesis, no, everything is the same. Well, I see differences, but I don't know if it's a big enough difference for me to reject the null hypothesis. I look at my calculated F value. So I go to the columns where down here at the bottom where it says ANOVA. That's the set of information that's actually useful to me. I go to the row that says columns there, row 17. Oh, okay. There are 3 degrees of freedom because there were 4 columns, which always take away 1, right? F score. The F on the columns is 41. Doing a two-tail test because it's either equal or not equal. Well, I want to know if I'm outside a critical value. What's F critical? 41's a lot bigger than 4, isn't it? Yes, I should reject my null hypothesis. This is statistically significant. Where I am changes my absenteeism. And then I can go back and I say, well, it looks to me like absenteeism is highest at plant 3 and 4 as opposed to plant 1 and 2. I've got averages of 20 and 18 at plants 1 and 2, but 29 and 25 at plants 3 and 4. That's method 1 to tell me I should reject this null hypothesis. What's method 2? I look at the p-value. The p-value under the columns is, which is a lot smaller than 0.05, right? And what I'm saying is that we're far enough out in this diagram that there's no way this just randomly happened to be that far out. And since we're doing a two-tail test, really I should double that number. 0.0004 is still really a lot smaller than 0.005. Even if I'd changed alpha to be 0.01, I'd still reject, wouldn't I? If I change alpha to be 0.01, my F critical values change. Nothing else in this entire pile changes. You run this test again and change alpha. Only thing you change when you change alpha are the critical values.
They wouldn't change alpha to 41.
Yeah, it's my reaction. It's not going to jump up to, but even if I didn't know that, even if I didn't know what the critical value was, if I change alpha to be 0.01, my p-value doesn't change. It's still smaller than 0.01, isn't it? It's smaller than 0.001. There's a 99.9% likelihood something funky's going on because it's less than 0.001, right? It's really unlikely that this is just, no, there's no real difference here. Smaller p-values mean there's more of an effect on your response variable. So there is a response change from the row, right? On the rows there it says 0.017 for a p-value. That means that it is had some effect. But since I didn't care about that, that's not important to me. And I could go back up here and I could look at the row data. And clearly, March 11th had more absenteeism that week on average than March 18th or March 4th. I don't know. The kids were on spring break. Nobody came to the plant. Whatever reason it is. A larger difference between my F value and my critical value. That's got more of an effect. Notice in the rows, F is 8.6 and the critical value is 5.1. They're still different, but they're not hugely different, like 41 and 4.7, right? Both have an effect, but I only cared about the effect due to the location. That's what made this really a one factor, and that weekend was a control variable. Just in case there was one weekend with really weird absenteeism, I took multiple weekends, but I didn't care which one it was. They were all Fridays. All I cared about was the absenteeism on Friday, different by location. Questions? So the bigger question is, how do I set these up? How do I make a decision as to whether or not something is an important variable or it isn't? We'll come to more about that. Let's switch problems. Problem 23 here. Problem 23, we're driving from the airport to a downtown hotel. 4 different hotels downtown have drivers that measure the drive time from the airport for 5 different Uber drivers. Does this sample provide sufficient evidence to conclude there is a difference in treatment? As soon as they use the word treatment means, I have to decide, do both rows and columns count, or do only the columns count? We'll look at it both ways. Because what I've got here is I've got 5 drivers, I've got 4 different hotels. So I could say, hey, which hotel you're going to, might that make a difference in the drive time? All the hotels are downtown. Maybe one of them is easier to get to than the other one. I don't know. You've got 5 drivers. Does driver choice make a difference? I don't know. Maybe you are driving under the Ubers run by Dr. Leadfoot. Or maybe it's grandma who only drives this car on Sundays who doesn't want to scuff the paint. I don't know. But we can find out. So, again, there's a data file for this one. This one's labeled drive time. Pull it up. Now, I'm using Excel because almost every business facility in the world will have access to Excel. You can do this in dozens of different statistic programs. As it says over there in the note, our data, we're using the one in the table, but you could just as easily use the data in that vertical stack. And different programming languages like R or Minitab prefer their data to be delivered that way. So this is where the analysis part, the person who is the analyst, makes their money. They clean the data to get it into a format where you can use it. But if you know how to do that, you can save that consultation money and put it in your pocket. So, I need you to tell me, run the ANOVA, and tell me whether or not driver choice matters, hotel choice matters. And let's do it at alphas 0.05. So, you got the data file. You go to the data tab, the data ribbon in Excel. And all the way over here on the right, it says data analysis. We're going to do an ANOVA 2-factor without replication. Same test we did moments ago. Tell it where the data is. You highlight this table again. Alpha's 0.05. Tell me, Does my choice of hotel matter? Why, Katie? Okay, wait a minute. Say that again. Okay. Driver choice is, sorry, hotel choice, right? I said hotels? Hotel. That's rows. Notice I did not select the labels this time, so it didn't put anything. It just says row and column. It was my mistake. So if I look at the rows here, there's a big difference between F crit and F. Yes. P-value is, and that means I can't reject the null hypothesis. So does my row effect make a significant difference? No. As far as I can tell, which hotel I am choosing doesn't affect this. I want either F to be much bigger than F crit, or I want P to be small. When P is large, I'm stuck in that middle unshaded area and my brain goes, crap, I don't have enough evidence to say those differences matter. What about the driver? I'm sorry, what was that on? F and F crit are almost identical. P-value, 0.050006. Holy moly. 10, 100,000, point, it's 6 millionths of a difference. This is one of the finest hairs I am going to split. Even looking at this, I don't have enough hair to split like this. Dude, according to that, P is bigger than 0.05. I should not reject the null hypothesis. But by the skin of my freaking teeth, this is truly right on the borderline. My choice of driver doesn't affect. But oh, is this a just barely? So here's a legitimate question. If I go back up there and I start looking at the columns, drivers are the columns, according to this over here. Ooh, wrong button. According to this, drivers are the columns, hotels are the rows. So here's my column information. Just look at the averages. Oh, yeah. Driver 5 is significantly faster than driver C is significantly slower than driver E. But on average, all averages compared, if I compare all 5 different averages, it is so close. If we changed our alpha from 0.05 to 0.06, we would reject this, wouldn't we? But again, that's a matter of how significant is significant enough. Is there a practical difference between taking 29 minutes to get to the hotel or 24 minutes to get to the hotel from the airport? I mean, here in Pittsburgh, it would be insane to try and get from the airport to downtown in 25 minutes. I've seen Green Tree Hill. No. So if it's not practically significant and it's just barely on the edge of statistical significance, there really isn't an effect for me to match up here. So I would say, and this is a judgment call, it's a borderline case. Now, borderline cases are what analysts get paid a lot to look at. You will be asked questions. Yes, I know it's right on the edge of whether this matters or not. Should we invest the money to improve driver speed? Would you make an investment here? Try and make those averages match closer? It's just barely making a difference right now. I'm not sure it's worth it. But if you were 0.04999, they would have said, yes, they make a difference. But again, just barely. That's a statistically dead heat. Really, absolutely not a statistical piece. It's a judgment call at that point. And that's problematic because without some experience to go behind that judgment call, I wouldn't know how these drivers behave except for these 5 individual samples, right? And we only took one time for each driver to each hotel, yes? Wouldn't it make more sense to take more times? If I had more data, I could look not just for effects between treatments, but I could look for effect and variation within the treatment as well. So that would mean I'd need more data, I'd need different data, I'd need to increase the number of things in each box. Well, that's a different data gathering situation, but the analysis allows for a little bit more precision in that fashion. I've got 3 more pieces of that. My data starts to look very different. So instead of 1 number per box, I have, in this case, I've got 4 numbers per box. I think this is going to take too long. We're going to put this off. So 2-factor ANOVA with replication is what's left, right? I've got that for another day, which means I'm going to be very generous to you people. Yeah, well, in this case, I would actually say that here, that is what told me that the rows didn't matter. I took the rows into account. Does your choice of hotel affect your drive time? No. Does your choice of driver affect your drive time? No. So I took both into account this time. But I didn't know in advance until I was talking about in that last one, I said, we're only looking at absenteeism by place. In this one, we were looking at drive time, both by choice of hotel and by choice of driver. So I wanted both to take accounts. You're welcome. That's the design of the problem. Ask the question in a way that I know, do I only look at the column? Do I look at both? In this case, the way they asked it is to look at both. But the statement is there a difference in treatment means, what's the treatment? Well, the treatment was only by plant. Here the treatment is both driver and hotel choice. So, Friday's our exam. I have the same set of tables. You get a handwritten single page. It shouldn't be the same page. If you need that stuff as well, feel free to make it more stuff on this page so that but you can use both of them when the final rolls around. So I would make a new page this time. And if you have to duplicate some stuff, that's fine. If you've got questions, email me. I have online office hours tonight, but I will be on campus. I'll be over in my office in Lynch if you want to stop by between 7:30 and 9, or jump on that Google Meet the same way you can. Or email me between now and tomorrow. The homework key will go up in about 2 minutes. I will see you all on Friday. Have a wonderful rest of your day.